Here's a review for test number 2. In test number 2, you can expect 4 or 5 questions covering the following topics. Since the last test, we covered edge interrupts, time interrupts, analog sensors, both in terms of hardware and software, digital sensors, mostly using software, LCD graphics, and random and matrix libraries and routines. Now, test number 2 will be just like test number 1. It's available in person, 50 minutes, work the problems in any order. You're able to backtrack if you want. If you take it on Blackboard, it'll be 100 minutes, random order with no backtracking. You must submit your answers to the first problem to move on to the next problem. And there's extra time on Blackboard just because you cannot backtrack. It takes time to download the problem, solve it, scan, upload your problems. Kind of a hassle. So it's either way you want to take it, your pick. Now the topics on the test. The first test covered Python programming with the Raspberry Pi Pico. This one's going to add to the topics, or add to the content of the first test. Since our first test, we covered edge interrupts. Now edge interrupts can trigger on the rising edge or falling edge. For example, I could have an up counter. What happens here is that when I push a button, the line idles high. When I push the button, it goes low. So on this code, I want to count every falling edge. The way you do that is you first define the pin to be input. Here I'm going to count the edges on pin 15. I define the interrupt service routine. When the interrupt happens, I'm going to increment a counter and set a flag. Note that with interrupts, I pretty much have to use global variables, but the only way to pass data between a subroutine that you didn't call and the main routine is through globals. Everybody can see globals, including the interrupt, including the main routine. I then have to initialize the interrupt. So this says that pin is an interrupt. It's triggered on a falling edge, and the options are either rising edge or falling edge. And when you interrupt, call subroutine count. That's up here. Then in the main routine, it looks like n isn't changing. That's the magic of interrupts. In the background, every time I see a falling edge, the interrupt is triggered. It increments n, which shows up in the main routine. Another type of interrupt is you can have multiple interrupts running at the same time for rising edges or falling edges. If you want to trigger on both rising or falling edge, then when you set it up, I do trigger is rising or falling. On the interrupt service routine, I actually have 2 interrupts running. On pin 15, I call channel A. On pin 14, I call channel B. And the logic, for example, for an optical encoder, on the rising edge of A, if B is low, I count up. On the falling edge of A, if B is high, I count up. So when I trigger the interrupt in this case, I don't know whether A is high or low, because I could trigger on both the rising edge and falling edge. That'd be an if statement. If A is high, that was a rising edge interrupt, and B is low, then I count forward. If A is low after the interrupt and B is high, that's also counting up. Second type of interrupt are timer interrupts. There are 2 types of timer interrupts. There's periodic and one-shot. On periodic interrupts, they just happen over and over again. For example, if we want to output a square wave, that'd be a periodic interrupt. This is a sample of code that interrupts once per second. To set up a timer interrupt, I have to import timer from machine. I then pick your variable. This is going to be timer interrupt, Tim, as in the mighty Tim. The interrupt service routine, every time 1 second elapses, I'm going to increment a global variable. This initializes the timer interrupt. This is Tim is an interrupt. I'm going to initialize it as a timer interrupt. The frequency is 1 Hertz. It's a periodic interrupt, happens over and over again every one second. And the interrupt service routine is called tick. Once again, the magic happens in the background. It looks like n isn't changing. In the background, once a second, tick gets called and n increases. A second type of interrupt is a one-shot. With a one-shot, the interrupt is only called once, For example, when I push a button, I want to output a pulse that's precisely 100 milliseconds. I can do that with a one-shot. So here what the main routine does is I wait for the button push. So while the button is low, I wait. While it's high, I wait. On the falling edge, I then execute the code. On the falling edge, I'm going to set the buzzer to 1 and then set up a timer interrupt. To do that, I have to once again declare Tim to be timer type interrupt. Define the interrupt service routine. Every time it gets called, I turn off the buzzer. And to call the interrupt, it's a one-shot, meaning it's only called once at 100 milliseconds, whenever frequency is the time that it gets called. And the interrupt service routine is called buzzer off. So 100 milliseconds later, the interrupt gets called and the buzzer gets turned off. Third topic we covered were sensors. Now with sensors, there's both digital and analog. With analog sensors, if the range is a voltage and it's large enough, I can read it directly with the Pi Pico. Oftentimes the range is too small. For example, if the voltage is going to be something, say 1.5 to 1.6 volts, that's not a very big spread. If I want to amplify it to 0 to 3 volts, I oftentimes use an instrumentation amplifier. So what this one does is the gain is R1 over R2 times A minus B. So the Y is R1 over R2 times A minus B. That's a differential amplifier. If I want to do this, essentially what I want to do is have a gain, put 1 volt becomes 3 volts. I want a gain of 30. I want the output to be 0 when the input is 1.5. So I would feed the signal into A. There's your data X. This is 1.5 volts, my offset. And I want the gain to be 30. So this could be like 300K, 10K. And oftentimes where you generate this voltage is the voltage divider. I've got a sensor. As the parameter changes, the resistance changes. As resistance changes, voltage changes. If that's the voltage, going between 1.5 and 1.6 volts, I connect it to my amplifier so that now the output goes 0 to 3 volts. In terms of calibration, that's taking the analog reading and converting it to something meaningful, like temperature, ohms, lux, whatever. On the A to D converter, it reads as 0 to FFFF, 0 is 0 volts, FFFF, or 65,535, is 3.3 volts. If I have a voltage divider, given voltage I can find a resistance. If I know resistance, I can find temperature. Or if it's a TMP36 sensor, if I know voltage, I know temperature directly. Just do a little bit of algebra, and given what I've measured, calculate what I want to know. Temperature, voltage, or temperature, resistance, lux, something like that. Second type of sensor we looked at are digital sensors. Some of these have standard interfaces like SPI and I2C. That'd be like the BME 280, GY521. We were using I2C to read those. For those sensors, you can use bit banging if you really want. Typically, you just use the built-in functions in Python. Or, if you're lucky, there's already a routine written that will read those sensors. Sometimes the sensors have a non-standard interface, like the HT11, HT22. For these sensors, they just have a single wire interface, and the data is sent as ones and zeros. The encoding is a 0 is a pulse that's 26 to 28 microseconds. A 1 is a pulse that's 70 microseconds. So by measuring the pulse width, I can tell whether the data is a 1 or a 0. And with that, I can start reading the data as a 0, 1, 0, 0, keep on going. In this case, after 40 bits, I've got my reading from the sensor. Then pull off the temperature and humidity. We also looked at the LCD graphics display. There's a bunch of Python routines and the LCD library. such as I can send text to the LCD display, I can draw lines on the display, I can draw a box on the display. We looked at the random library. The random library just has a limited set of functions in MicroPython. I can generate a random integer between a and b. I can generate a random integer between in the range of 0 to 1. I can generate a random number between a and b with step size dx, and I can generate a uniform distribution, a floating point number between a and b. With those, I can generate other types of distributions like exponential, Poisson, Pascal. And finally, we also looked at matrices. Now, matrices are really useful. Python is similar to MATLAB, but the way they handle matrices in Python is very different. In MATLAB, if I say A is matrix 0, B is 5 times A, then B is 5 times 0, also 0. In Python, B is going to be 5 copies of A. So in Python, you have to write your own matrix routines to add, subtract, multiply, and divide matrices, because Python doesn't do it right. Well, it doesn't treat your variables as matrices. If you do that, I can do more complicated routines, like do least squares curve fitting. It's not as convenient as MATLAB, but it does work. So that's kind of the topics covered on test number 2. The strategy on test number 2, when I write it, is the problems have to be simple enough that they're not trivial. Well, they have to be complicated enough that they're not trivial, but simple enough you can solve each problem in 10 minutes. Because if you have 50 minutes to solve 4 problems, you can't be spending 2-3 hours on one problem. So that's the challenge for me on writing the test. Come up with 4 or 5 problems that kind of gives a sampling of these topics that's where each problem isn't trivial, but doable in 10 minutes. And that will be the test on Friday. Again, the test is available 6 a.m. till midnight. And good luck on the test.